Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 27, practice session 9, in which we will solve our next problem, 28, in which we are given a circle S0 shown in yellow and two distinct coplanar points, A and B. The mutual juxtaposition of the input objects, of course, can be anything. This is just a simple illustrative example. And the challenge of the problem number 28 is to construct all circles such as a simple circle sigma shown in red that pass through the two given fixed coplanar points A and B and intersect the given circle S0 at a given ahead of time angle theta 0 and the angle between two intersecting cooperating curves. As a friendly reminder, is defined as follows. First, we construct a straight line, such as the straight line tau S0 shown in yellow that is tangent to the first object through the point of interest, and then we construct the second straight line, such as the straight line tau sigma shown in red that is tangent to the second object at the same point of interest, and these two straight lines will partition the parent plane into four regions, 1, 2, 3, 4. These four regions can themselves be partitioned into two sets of two regions, and within each such set, the corresponding region defines the angle of one and the same magnitude. And across these two sets of regions or angles, we have the larger angle, for example, this one, and a smaller angle, this one and this one. Consequently, the angle between two intersecting and cooperating curves is defined as the smallest angle between the corresponding tangents drawn to the objects that intersect at the point of interest. Before we step into the weeds of the solution of the problem number 28, a few words about the emphasis of this episode, which is, recall that the way we learn mathematics in any of its domains whatsoever is as follows. First, we sit at the bottom of the mountain, we spend some time trying to figure out the basic ideas, the basic notions, the overall philosophy, for example, of this or that discipline, and then we try to start climbing the technical knowledge that is associated with that layer. We do it for some time, and then we reach the plateau at which we start solving problems in this particular area. This is precisely the area right about here when we become dangerous, because we know just enough to inflict a certain amount of damage on any given problem. Usually we mess these problems but good, and eventually we succeed. And right about this time right here, so in this time frame, this is when the semester or the academic year ends. We pass our exams, we tell the examiner our side of the story, we get hopefully a good grade, and we move on. And at this point, in the corner of our mind, we say, yes, I now know the theory of groups, I now know the theory of graphs, theory of numbers, differential geometry, analytic geometry, differential equations, integral equations, Fourier analysis, on and on and on. But in actuality, nothing can be further from the truth. We do not really know that much about this or that layer of mathematics on which we just took one course, for example, one semester or even 2 semesters. And this is exactly the problem with the way we study mathematics, because the real knowledge, the real understanding of any given layer in mathematics happens if we undertake that journey replicated many times. Run along the plateau, climb up, plateau, climb up, plateau, climb up, and so on. So the real learning of mathematics happens exactly over here, and that area, stretches over many, many years. And this is where we come back to the idea that I put forward in the previous episode. And unfortunately, when I say these words, they do not really carry that much weight because, as I said before, this channel has nothing to do with me personally. It's not about my personality. This channel has only one goal, and that is exercising the art and the craft of hard sciences for the sole sake of exercising the art and the craft of hard sciences. And I hope that when the figures of authority say pretty much the same words, then these words will carry more weight. And in that respect, recall that in the previous episode, I claimed that no solution of a worthy mathematical problem or a proof of an interesting theorem is ever complete, or as George Poya puts it, ever exhausted. All such solutions or proofs can be dissected in many different ways, in many different segments, if you will. Each such segment can be partitioned further and further and further, and that means there is always plenty of material to cover and plenty of different ways to look at one and the same solution or one and the same proof. And just to make sure that you hear this from some more authoritative figure, here is what George Poya, the author of the immortal book How to Solve It, has to say about it. In that book, How to Solve It, I will put this text for you on the screen for about 5 seconds, but my suggestion is that you put this video on pause, try to read the entire quote and comprehend it, think about it, and only then move on, because there is absolutely no rush here. And the other figure of authority, Terry Tao, puts the same ideas expressed by George Poya that you just read in a different way. His motto or his mandate is to learn and relearn. And in our case, Terry Tao's learn and relearn mandate means that we really have to solve many, many problems, and we have to keep solving many, many problems until we put the technical essence and the ideas behind the methods and the tactical knowledge that we're studying currently into our bone marrow, and we do not really go through any effort. In other words, we unconsciously manipulate the material that we're studying, and especially the methods, or when we combine the technical knowledge with the methods that apply in many different areas of mathematics. And that is, for example, the problem-solving approaches such as transform and conquer, reinterpret and conquer, divide and conquer, eliminate and conquer, reverse order, scope expansion, scope reduction, invariant equation, and so on. And again, the idea is to solve so many problems as to make sure that we do not make any conscious effort in order to manipulate these notions and ideas. And in this particular case, in this particular practice, we will apply this idea to the combination of the following two problem-solving approaches: reverse order and transform and conquer. That is correct. We have seen this type of a problem before in episode 14, seminar 5, problem 15. We were asked to construct a circle that was orthogonal to a given circle, let's say Q, and that passes through two given coplanar and fixed points A and B. And as a friendly reminder, here is what a professionally made construction for the solution of this problem by me using the free software called GeoGebra look like. And here's a fragment of me carrying out the explanation of the solution of the problem back then in episode 14. And those of our viewers who have put in an honest effort to solve this problem, will have no problem recalling the technical essence of our solution, which was what? The technical essence of our solution was to reflect the point B, let's say one of these points in the given circle with positive power into its image B prime, to reflect the point A, the other point, in the same circle with the positive image into the point A prime, and then construct the perpendicular bisectors of the corresponding line segments, and the point where these bisectors intersect exactly mark the spot and produce the center of the circle that will be orthogonal to the given one and will pass through the given points. And why did we do that? Well, we did that because precisely of the theorem number 39, according to which any circle that passes through 2 points that are the inversive images of each other with respect to a certain circle, such as the circle Q, will be what? Will be precisely orthogonal. Will be orthogonal. The circle omega will be orthogonal to the circle Q. As such, in some sense, and echoing back to the ideas that I just discussed in the previous segment, what we have in the problem 28 is a generalization of the problem number 15. Why is that? Well, in the problem 15, evidently, the magnitude of the given ahead of time angle theta 0 is precisely over here in this problem. Theta 0 is precisely pi over 2. But because we took care of the case when the magnitude of the angle theta 0 is pi over 2, now we want to consider the cases or generalize our problem then when the magnitude of the given ahead of time angle theta 0 belongs to the open subset of real numbers and its magnitude is strictly larger than 0 and strictly smaller than pi over 2. Again, this goes back to the definition of the angle between two intersecting curves as the smallest angle between the two corresponding tangents. We took care of the case when the angle theta 0 is equal to pi over 2. So here the magnitude of the angle theta 0 is strictly smaller than pi over 2. Implementing Terry Tao's mandate of learning and relearning, we want to keep solving problems in the given layer of mathematics that we're studying right now, which is the inversion of the real plane with respect to a circle, over and over again until we put all the technical essence of inversion of the real plane with respect to a circle and the corresponding problem-solving approaches into our bone marrow. We burn that technical essence into our upper crest of the brain, and we make virtually no conscious effort, or in other words, we manipulate this information unconsciously, almost unconsciously, when we work on the solution of a problem. So how does the reverse order problem-solving approach apply to our problem? Well, in our case, we make an assumption that at least one solution circle, such as the circle sigma shown in red on the left side of your screen, exists, and such a circle passes through the two given fixed distinct points A and B, which are coplanar with the circle S0, and that circle intersects the given circle S0 at a given angle theta 0 that sits between the magnitudes of 0 and pi over 2 exclusively. The magnitude of the angle theta 0 is strictly larger than 0 and strictly smaller than pi over 2 for the reasons explained earlier. And now the next idea is to craft or make an attempt to craft a chain of if P then Q implications that take the artificially solved state of our problem all the way back to the unsolved state. And the next question is, what's such a chain that takes our problem that is in the artificially solved state and then moves it into the original not solved state, B? Well, let us think about this together. If circle sigma, such as the circle shown in red over here, is a solution circle, then we can craft our first implication as follows. if this circle is a solution circle, then it must pass through both points A and B at the same time. What does that mean? It means that if any circle intersects the given circle as a given angle, but does not pass through both of the points A and B, fixed, distinct, coplanar with the given circle, then such a circle is not a solution circle, and such a circle can pass only through the point A but not through the point B. No good. Such a circle can pass only through the point B but not through the point A. No good. Such a circle can intersect the given circle as 0 at a given angle but do not pass through either of the points A and B. No good. In other words, our first implication is the following: if a circle, such as the circle sigma, is a solution circle, then it passes through 2 points A and B at the same time. And once we have that, this is the moment of time when we combine the reverse order problem solving approach with another problem solving approach, which we call transform and conquer, using the immediate tactical knowledge of the mathematical layer that we're studying right now, inversion of the real plane with respect to a circle, as a bridge. In other words, what kind of theorem comes to mind over here? Well, either for the point B or for the point A, it doesn't really matter. For demonstration purposes, let us assume I'll take the point A. We will make the point A carry the jacket of the center of inversion, and the radius of such inversion can be anything, any legal number, strictly positive real number. The actual magnitude of the radius of inversion or the length of the radius of inversion is irrelevant. And here we can craft the next implication. If a circle sigma passes through the center of inversion A, then under the inversion of the plane with respect to a circle centered at the point A with any strictly positive real number r as its radius and positive power, such a circle will be taken into a straight line sigma prime. So under the inversion of the plane with respect to a circle lowercase c, I do not show this circle explicitly on the drawing in order to avoid the clutter, and in some sense we do not really need that circle in our mind's eye. We can see already what is going on. We know enough of technical information, we solved enough problems, we do not really need it. All we need to know is that the center of inversion is the point A, and the radius of inversion is any strictly positive real number r. It doesn't really matter. The power of inversion is positive. The composition of inversions is very straightforward. It's trivial in some sense. There is only one inversion that is enough, and this is our second implication, if P then Q implication. If a circle, such as the circle sigma, passes through the center of inversion, then it is taken into a straight line sigma prime that does not pass through the center of inversion, and conversely, such a straight line sigma prime that does not pass through the center of inversion under the inversion specified will be taken into a circle that does pass through the point A. That is the first implication. What is the second implication? Well, in this case, if this and that, then look at this. The given circle as 0 does not pass through the center of inversion, and that means that it will be taken into a genuine circle S prime 0. What's the third implication? Well, the third implication is that if we have the point B sitting over here, then under the corresponding inversion, that point will be taken into the point B prime. And in which way do all these reflected objects interact with each other? Well, remember that inversion of the real plane with respect to a circle equipped with the point at infinity is a bijection. To each point that is the pre-image, it corresponds a certain image, and conversely. And we know also that if the point B does belong to the solution circle, remember this is our first implication, then the image of the point B will belong to the image of the object to which this point belongs. The image of the object to which the point B belongs is a circle's straight line sigma prime, the circle sigma straight line sigma prime. That means that the point B prime will precisely belong to the straight line sigma prime. And not only that, one more unit of theoretical knowledge that we need over here in this wonderful combination of reverse order and transform and conquer is the fact that the magnitude, but not the orientation or the direction of angles under any inversion of the real plane with respect to a circle is preserved. That means that no negotiation over here, no room for any games. Our straight line sigma prime will intersect the circle S prime 0 at an angle whose magnitude is equal precisely to theta 0. The direction of this angle, if we were to keep track of directions, will be flipped to an opposite, but the magnitude, the absolute value of that angle under which the straight line sigma prime and the circle S prime 0 intersect will be the same. That much we guarantee. And now we have arrived at the unsolved state or not solved state of the problem, because look at this. Right now we can throw out, if we throw out this straight line sigma prime because we do not have it in the original state, we have an equivalent problem, equivalent of the original problem, which is not solved state. But in this case, this is exactly where we gain the competitive advantage, because the transformed problem, or the transformed equivalent of the original not solved problem, is in some sense much simpler, or we can also call it a primitive problem or a previously solved problem. This is a building block for the next more difficult problem, and once we solve this problem, it will become primitive problem for the next step. In another, perhaps even more difficult problem, this will be a previously solved problem, and on and on and on. This is how mathematics works in general, a wonderful way in which mathematics works. But in our case, if we throw out the straight line sigma prime, then we have the equivalent of the original problem in the unsolved state, and our chain of if p then q implications that started or originated at the not at the solved state came back and terminated at the not solved state. And what does this not solved state say? Well, we have the following setup. Given a circle such as the circle S prime 0, which is the equivalent of the original circle S0, and given a point such as the point B prime, which is the equivalent of the point B, we also have the angle theta 0, construct a straight line such as the straight line sigma prime that intersects the given circle S prime 0 at a given angle theta 0. Observe that through the magic of the combination of the reverse order and the transform and conquer problem-solving approaches, we managed to take a difficult problem to an equivalent, simpler problem as follows. We managed to replace a difficult-to-construct object, such as the sample solution circle sigma, with a much simpler-to-construct object, which is the straight line. And we also managed to reduce, amazingly enough, the number of points which introduce a constraint to a given problem. Instead of 2 points, we now deal with precisely 1 point. And I recommend that you put this video on pause, walk away, and think about how this magic unfolded in order to understand how exactly did we gain the competitive advantage. A simpler to construct object, a straight line, and the reduction of the number of points through which the object this has the requested properties must pass, because there is no rush over here. Take your time to understand what is going on. But now this is precisely the time where we conquer. Reverse order, transform, and conquer. Now we conquer. And how do we conquer? Well, look at this. The straight line, such as the straight line sigma, can intersect a quadratic curve in at most 2 distinct points. And in this case, our straight line sigma prime does intersect the image circle S prime 0 at 2 distinct points. This point right here and this point right here, and both of these points are equidistant from the center of the image circle S prime 0, which for now we do not have. How do we find the center of the circle? This is an optional segment for those who do not know how to locate the center of a given circle. Listen up. This is basically the Euclid's Elements book 3, proposition 1, the very first proposition with which Euclid opens the development of theory of circles, and the construction unfolds as follows. Given a circle, we pick any 2 distinct points on that circle, for example, this point and this point, we snap a straight line through these 2 points. We thus construct a chord of a given circle. Then we construct a perpendicular bisector of that chord right here, right angle, equal length through this point. And it turns out that the perpendicular bisector of an arbitrary non-zero chord of a given circle will intersect that circle at 2, this time diametrically opposite points. And what does that mean? That means that if we construct another perpendicular bisector of this perpendicular bisector, like so, we will precisely nail the center of that circle O, because the angle between these 2 straight lines is right here, and the length of this line segment is equal to the length of this line segment, radius of the circle, diameter of the circle, the center of the circle. Now that we know the location of the center O of the image circle S prime, what we do is we connect that center with the point, any one of the 2 points where the straight line sigma prime intersects the image circle S0. This point or this point, it doesn't really matter. You can pick any one. For demonstration purposes, I pick this one and I name that point X, precisely because we're still in some sense working in reverse order. This is miniature reverse order problem solving approach, because we right now want to find a way in which we can construct the straight line sigma prime. And to that end, we need to know the location of the point X. And this is how we recover it, again, by assuming that we have the straight line sigma prime constructed, and we see what kind of tactical gold or technical advantage we can dig up if we assume that the straight line is already constructed. So what we have here is the following. We have the radius that originates at the center O of the image circle S prime. It runs into the point where the straight line future to be constructed straight line sigma prime intersects the circle S prime 0, the image circle, and to that radius we snap a straight line that passes through the point X perpendicular to the radius. That straight line is shown over here in yellow. I named it tau because that straight line is the tangent to the circle sigma, S prime 0 at the point of contact. And why did we do that? We did that because this is precisely, remember, this is precisely the definition of the angle between 2 geometric objects cooperating and so on. And how do we measure that angle? Well, across 2 angles, remember, we pick the smallest one by magnitude. So in some sense, to be totally pedantically correct, the members in the audience will keep me honest, we have to put the absolute value of this angle will be the same, not the direction, by the absolute value of this angle will be the same, and we measure it as follows. For example, for demonstration purposes, again, here it will be on this side and on that side. These angles are vertical. Remember our partitioning argument: 2 intersecting straight line, 4 regions of the plane, partitioned into 2 sets of angles of equal magnitude, and on and on and on. So from 2 larger angles, we pick the smaller one. So here, the angle theta 0 will be this and this. Precisely, again, remember that the reason that this is the fact, this and this, is because any inversion of the real plane with respect to a circle under any power, positive or negative, preserves the magnitude of the angle. So that means that if we have this straight line, sigma prime, intersect the image circle S prime O at a given angle, this is precisely how we do it. This is the technical essence of this definition: intersection between the straight line and the circle. But now look at what happens over here, the amazing situation. If this angle is theta over here, let's concentrate on this part right here, you can see it here, then by definition the angle between the radius drawn from the center of the circle to the point of tangency with the tangent tau will be what? Necessarily a right. This is another fundamental fact. But that means there is a little angle over here. The angle, let's say we will call it OXB. I showed it with 2 red small arcs and the arrow points over here. What is the magnitude of that angle? Precisely, the magnitude of that angle is pi over 2 minus theta. And in some sense, the problem is solved. Why is that? Well, because now we have another wonderful little line segment over here. Look at this. We connect the lines, the points O, the center of the circle, and the point B prime. We connect it with the line segment. And now we have the following smaller yet miniature problem, which is the primitive problem, again, the building block of the solution of this problem. What is the set of points in the parent plane from each of which the given line segment, such as the line segment OB, is seen under a constant or one and the same angle, alpha, which is pi over 2 minus theta 0? Well, we know the answer to that question. This is one of the classical problems in geometry, and actually that object that is the answer to that question in grown-up mathematics is called a cycle, and it plays a fundamental role in the construction of non-Euclidean geometries. And to that fact alone, I can put together another course, but that is a different story. The idea here is the following. First, why do we claim that with Euclidean tools alone, a compass and a straight edge, which is a requirement in all the problems in this course, and the requirement of the problem 28, we can solve this particular problem? Well, first of all, can we construct this algebraic relation over here has its constructive sibling. What is this constructive sibling? Well, it is quite straightforward. Look at this. We draw any straight line whatsoever. At some point that we pick on that straight line at random, we snap a circle. This circle will intersect the straight line at two diametrically opposite points. And again, all we have to do is cover the distance that's more than the radius. So we open up, we put the needle of the compass over here, we open up to this distance, we draw a circle here, we swap trade places, we put the needle here with the same compass, we open over here, we have two points over here, and if we draw the straight line, this straight line will be perpendicular to the original one. Boom, we have our angle pi over 2. We have the angle that is right. Now, how do we copy? Let's say we have the angle of the given magnitude, theta 0. This angle right here is theta 0. How do we copy this angle into any location in the parent plane with Euclidean tools alone? Well, we can do it basically with a compass alone. Stick the needle of the compass into the vertex of the given angle and draw a circle of arbitrary radius. Boom. Still with the compass open, carry it to the point of interest over here and snap that circle right here. We will obtain this point right here. This is the image of this point. Then we bring the compass over here, put the needle, and we draw another circle over here through this point. We cover this distance. And then keeping the compass open, just like that, we carry it over here, snap the circle, boom, we have our point, and here we have an exact copy of theta 0. The proof that this is the case is left to the viewer as an exercise, but as a hint, you will use side congruence of triangles criterion. But now we know that we can construct the angle alpha with the compass and the straight edge alone as it is required. And now we can answer the following question. What is the set of points in the parent plane from each of which this here line segment B prime O or OB prime is seen under one and the same angle? Well, the answer to that question, like I said, is the construct that is called a cycle. In mathematics, let's say this is our sample line segment, and if we keep the angles unsigned, or we do not care about the direction, then the shape of this figure will be as follows. This will be two circular arcs that share this line segment, as their common chord. One portion of a circle and the other portion of a circle. This will be two absolutely symmetrical circular arcs, and this is the answer to our question of what is the set of points from each of which this here line segment is seen under the angle one and the same constant angle alpha, which in some sense, if you are willing to ignore this fact, is the magnitude of the angle theta 0. And for those who do not know how to construct this so-called cycle, or the set of points in the parent plane from each of which the given line segment is seen from under the same angle, here is a very short explanation. A cycle in Euclidean geometry actually can be constructed in a number of different ways, and here is perhaps a simplest way that I can muster. So let's say we're given our line segment, such as the line segment OB prime. So this is our line segment right here. Positioned like so, for example, it doesn't matter. We already explained how to carry the magnitude of any angle in the plane with Euclidean tools alone. So what we do here is the following. We pretend that this line segment belongs to an extended straight line in some sense. And then this is our straight line shown over here. So we need to construct the magnitude. Well, in this case, it will be the angle alpha, this magnitude right here. So let's say we constructed the angle like so through this side. It doesn't really matter through which side. Again, you can do it through this side or through this side. Let's say we constructed it through this side, and this is our angle right here. This is our angle by magnitude alpha. This is our angle called alpha. This much we understand. This is angle alpha. So what does it mean already? Can you figure this out on your own, quickly on your feet? Well, you should. This is the tangent. This is the chord. So we bring in book 3. Remember, we used it in the previous episode. Book 3, proposition 31. It's the angle between the tangent and the chord. So here we reconstruct the center of one interesting circle as follows. We construct a perpendicular through this point to this straight line, perpendicular like this. See? Boom. And we already explained how to do it. This can be done completely with Euclidean tools alone. And what is next step? 1, 2, 3. I cannot hear. Yes, we bisect the given line segment with the perpendicular bisector. Angle equals sides, equal length line segments. The point where these two straight lines intersect, perpendicular to the line that forms the angle alpha and the perpendicular bisector of the given line segment. Boom, marks the spots. This is, we draw the circle of the given radius. And if you want, stick the needle over here, flip this point over here. You have another one, stick the needle over here with this distance right here. You draw another circle. And voila, from any point on the circle on that side, this line segment will be seen by the angle alpha. This is the wonderful property of circles. This is the theorem that Euclid also proves. Alpha, and then from any point on this circular arc, this line segment will be seen again by one and the same angle alpha. You see, this is how straightforward this construction is with Euclidean tools alone. Here we will need a compass and a straight edge. One more time in the lightning round. Given line segment, one side that forms the angle alpha, perpendicular to this side, perpendicular bisector to the line segment, point, one thing, game over. Once we have this point, we'll locate its symmetrical point on the other side. One arc, two arc, and remember that these two arcs are absolutely symmetrical with respect to the given line segment. And as a short fun quiz or a question that will separate the members of the audience into those who do know and those who do not know, in Euclidean geometry, the set of points from each of which the given line segment is seen under one and the same constant angle that looks like figure 8. And also don't forget that the point that it does not belong to this set, the point that sits inside any one of these arcs or outside of these arcs, will not satisfy this constraint. So in Euclidean geometry, this figure 8 looks like what in non-Euclidean Galilean geometry. Remember, there are many non-Euclidean geometries. One such non-Euclidean geometry is known as the Galilean geometry, which is very closely connected with physics, that goes deep into physics. So in this non-Euclidean Galilean geometry, the figure 8 over here looks like what? Well, in non-Euclidean Galilean geometry, the cycle that looks like figure 8 in Euclidean geometry is a curve that is isomorphic to or indistinguishable from a parabola in Euclidean geometry. And like I said, this can be the basis of an entire course, but we digress. We now understand that we can construct the set of points from each of which the given line segment is seen under one and the same constant angle in Euclidean geometry, which is the foundation of this course. This set looks like a figure 8, and we know that our angle alpha is the difference pi over 2 minus theta 0. This algebraic construct known as a difference of two, let's say, real numbers has its constructive sibling shown over here. We know how to construct that number. We know how to carry the number into any location in the plane. We constructed these two constant angle arcs, let's say two constant angle circular arcs. The arc, where do I have the room? It will be the arc A1 and the arc A2. For example, we'll name this arc. We'll use the same color. It has the same color. This will be the arc A1. This right here will be the arc A2. These arcs, as I mentioned before, completely symmetrical with respect to the generating line segment. They will lie on either side of that line segment in a symmetrical fashion. So which one circular arc, such constant angle circular arc we choose to work from, A1 or A2, again, it doesn't really matter. They will all lead to one and the same answer for demonstration purposes. Let us work with the circular arc A1. It doesn't matter. So here we right away see already the conditions which will cleave our input material into that many solutions, or no solutions at all. So we put over here, let's say we work with the arc A1. We understand that it makes no difference. So if we have a couple if statements over here, if A1, the constant angle alpha circular arc A1 intersects the image circle S prime 0 at two distinct points x and y such that x is not equal to y, and such a configuration is shown over here on the right side of the board, then we know right away that this problem has how many solutions? Two distinct solutions, each of which corresponds to the point x and y. Let's say our circular arc A1 intersected the image circle S prime 0 at two distinct points, the point x, the point y. What do? Well, we now pretend that we do not have the straight line segment. The whole point of this exercise was to find a way to start with a given circle, S prime 0, the given circle, B0, and the given angle. And this is what we do. We construct this here configuration, the figure 8 in Euclidean geometry. We construct it with Euclidean tools alone because we know the angle theta 0, we know pi over 2, blah, blah, blah. We constructed these two circular arcs. We picked one, and voila, look at this. Point X, point Y. Well, we connect the point X with the point B prime. One straight line. Now I call it sigma prime 1. And we have the second generating point, Y. We connect Y with the point B prime. Snap. Sigma prime 2. And also don't forget, now it should be, of course, on my by hand, by eye drawing. It looks a little goofy. In a few seconds, I'll show you a professionally carried out construction by me using the free software called GeoGebra. But these points of intersection over here will be symmetrical. Let's say instead of the same or constant angle circular arc A1, we pick this one, constant angular arc A2. Well, here we will have this point and this point. This point will be the sibling of the point X, and this point will be the sibling of the point Y. So from this through this point, we snap a straight line through the point B prime, and through this one point, we snap another straight line through the point B prime. Either way, we will have two straight lines, two distinct straight lines, and if we reflect these two straight lines back via the same reflection that way, the same inversion that we picked over here, they will be reflected into two circles, sigma 1 and sigma 2. Another circle will run this way. Again, I don't want to clutter the construction more than I have to, but you understand that this will be another solution circle, sigma 1, sigma 2. Both of these solution circles will pass through two distinct fixed coplanar points A and B, and they will intersect the given circle S0 under the given angle. So if the circular arc A1 intersects the image circle S prime 0 at two distinct points, the problem has two distinct solutions. If the circular arc, same angle or constant angle circular arc A1, has precisely one point in common with the circle S prime, in other words, that arc somehow touches the circle, the image circle S prime 0, how many solutions then we will have? So here we will have, let's say this way, I'll mangle it a little bit, two distinct solutions, you understand? Here we will have one distinct solution, 1 point, one distinct solution. We take this point, we connect it with the point B prime, it will be one straight line. In some sense, these two straight lines degenerate into one. It will be one straight line. Reflect the straight line in the chosen circle of inversion, center, radius, everything is the same. Flip it back and voila, we have our solution circle sigma, one solution. And if the same constant angle alpha circular arc A1 intersects with the circle S prime 0 over the empty set, no common points between any of the circular arcs and the circle S prime 0, the image circle of our input circle is 0, then no solutions. So here, no solutions. And once we understand how all this underlying material was developed, we omit all this wonderful manipulations that we did, and in some sense when we prepare our solution for publication, we usually do not show to the audience all this dirty work, if you will, that we did. We only present a solution that flows in one coherent exposition. Do this, do that, do this, do that, and the audience is bewildered. How did the solution come about? Where did it come from? How it was generated? But this is exactly the point of this course. This is why I put it together, where the emphasis is not on writing polishing proofs, but the emphasis is on the mechanics of generating these proofs. How we can do it. Try and fail, try and fail, try and fail. Do not give up. Boom, persevere and find a solution. Once we find the solution, you will already, I trust you, I'm pretty sure you can polish the solution and present it in a nice way on your own. But now that we have it, just to be nice students of mathematics, I will erase this material, and in a few seconds I'll write down the steps that will be a version of an algorithm that solves the problem at hand. As I was preparing this segment of our practice session, I realized that it's better to keep the information that we generated over the course of this episode in front of us, front and center, so that we have a nice visual guide for this. But again, if you have any questions or something is not clear in my description, you can always look at the printed material. I have a link to the free PDF file that is a chapter of my free book, Inversive Geometry for All, on which this practice session is based, literally in 2 clicks. Click, click. You can gain access to that PDF file. Scroll all the way down. I have listed the steps of this algorithm over there, so you can go over it at your own pace and look at it in more details. But fundamentally, we understand now how the problem number 28 is solved, or how the solution of this problem unfolds. First, we reflect the point, let's say B, and the given circle S0 in the circle that is centered at the other point, however you decide to name this point. These points with positive power once into their images, the point B prime and the circle S prime 0. Step number 1. Step number 2, find the center O of the image circle S prime 0. We explain how to do it. Step number 3, construct a cycle on the line segment OB prime for the angle alpha, that is pi over 2 minus theta 0. Again, we explain how to do it. All these steps can be carried out with absolute certainty with Euclidean tools alone. You know how. Such a cycle will consist of 2 constant angle arcs, of which we only need to pick one, and we work with one. Let's say with this arc A1. So here we analyze the outcomes of the intersection of this arc, or we analyze the number of points that the constant angle arc A1 shares with the image circle as 0. If the number of such points is two distinct points, x and y, x is not equal to y, then this problem has two distinct solutions. And how do we obtain those solutions? Well, snap a straight line through the point b prime and the first point from the set x, and snap the second line through the point b prime and the second point in that set y. So take the straight lines xb prime and yb prime and reflect them in the same circle, back into the solution circles. Game over, two distinct solutions. If the constant angle circular arc A1 has precisely one point in common with the image circle S prime 0, I do not depict the situation, but let's say that point is T for tangency. In that case, that means that these two circles touch, and evidently they will touch internally. Then this problem has only one solution. We reflect that point, that straight line T B prime, because that's the one point in common between the arc and the circle T B prime, into the circle sigma. That circle will pass through the two given points and will intersect the given circle at the given angle. We understand how that works. And if the constant angle arc A1 intersects with the reflected circle S prime 0 over the empty sets, in other words, these two geometric objects have precisely no points in common whatsoever, then our problem has no solutions altogether. And here is how a professional solution in all its gory details will look like if it's carried out with a graphing software of your choice. I prepared this image for you using the free software called IGRP. And this concludes the solution of the problem number 28. This also concludes our episode and concludes this practice session. And as a fair warning, the next practice, the practice number 10, will be the final meaty, substantial, or tactically interesting session of this course. After that, there will be the final episode of this course, the farewell and good luck. And in the next and the final practice session, we will be solving the following interesting problem. So I'll give you a little bit of a fair warning and a heads up. You can think about it in your spare time. We will be given two circles that are not located one inside the other of distinct radii. So let's say we will be given a, let's say, large circle and not so large circle. And then the challenge in this problem will be find a way to reflect such two distinct radii circles into two circles that have the same radius. So perform some magic and then produce two circles that have exactly the same radius. Now, this is it for this episode. I will see you in the next and final episode of this course, where we will solve the final problem, number 29.